enough resources. Okay, so here we go. January 28, 2004. Trying to give you some arbitrary tests so that you haven't done that. That was my guess. So we're going to be crazy and start in order. Okay, and let's start with number 1. Yes? Sure. Our reference tables are thinning out. People like stealing them. Okay, I think someone has a 40 in their bag somewhere. All right, I don't know if you needed one. Got one. Yeah. Anybody else for a table of reference? All right, so let's see. These are falling apart, so. All right, rock on. Okay, here we go. Number 1. Let's make this up close and personal. Okay, a neutral atom contains cold neutrons and electrons, the number of protons in this atom. The key for me, party people, is the word neutral atom. In fact, they don't have to say neutral atom. It's kind of like saying it's an emergency, you have to go fast, obviously. When you say the word atom, you say atom, I say neutral. I say atom, you say neutral. Right, okay, so anytime you have an atom, my friends in chemistry, they're always neutral. So this is actually redundant, like saying Mr. Grodsky's tall. Mr. Grodsky, it's what to say. Of course I'm tall. So atom is neutral, so the protons always equal the electrons. So anytime you hear atom, any way you want to say it, you're thinking protons equal electrons. Now, they gave me electrons, so my friends in chemistry, it has to equal protons. That's what it is. An atom is always neutral, so I don't know why they even did that for you. A lot of times they don't. So this is a core concept. Somewhere in your test, and I've seen this as a part 2, where they've asked you, hey, why is an atom neutral in so many ways? And in part 2, they kind of like hide easy kind of answers. And I keep saying this in all my reviews, that they're the same answers, but different questions on different tests. So I've seen this in a part 2 where they said, explain to me why strontium, whatever, is neutral, and you say protons equal electrons. I've seen that in part 2. So in any case, atomic number is 11. All right, you should know that neutrons have the same mass as protons and all this other good stuff we can get from table O, but that's number 1 is 2 for that reason. Number 2. Isotopes. Stop. Iso means same. Also know where you are in the test. If you're starting with number 1 and 2, you're starting in atomic structure. The test from 1 to 30 starts from atomic structure, periodic table, bonding, mathematics, physical part of chemistry, eventually all the way through to nuclear. So know where you are in the test. You're not going to get a nuclear question here. So we're talking atomic structure. So think and expect certain types of questions in certain areas. It might help you. But here we're in atomic structure. They love to talk about isotopes. Isotopes of an element must have different what? Well, isotopes of an element are the same element. So real quickly, okay, you should know clearly that an isotope, and I'm just going to wipe this out for a second, okay, isotopes, all right, have to be like carbon-12 and carbon-14. Notice they're the same element. What's the same about them? What makes them the same is the proton number. What makes them different is different number of neutrons. How do you get neutrons? This number minus that number. Mass. Now the mass number is protons and neutrons. This is protons. So if you track protons and neutrons from protons, you get neutrons. So this is 6 protons and 12 minus 6, 6 neutrons. This is 14 minus 6, 8 neutrons. This has 2 more neutrons. Somewhere in your test, especially in a part 2, they love to look at isotopes and tell me how they differ. How many times in part 2 have I seen? And I want you to understand something. Part 2 is the same as the multiple choice. They're the same types of questions. And I've seen, say, explain, give me one similarity and one difference. I've seen that. They would say, well, similarity between isotopes is they're the same element, which means same number of protons. Atomic number is unique. What's different? Different number of neutrons. So isotope and L must have different number of not protons. They have to be the same element. Different number of electrons? That makes no sense. Okay, because elements are atoms, atoms are neutral. You say atom, I say neutral. Atom. Neutral. Oh, whatever. Okay, now, so, okay, I messed that up. Never be a dance party host, which is actually a DJ, right? In any case, see how old I am. In any case, the party, so atomic number is the same because that's the proton number. So number 2 is atomic number, all right? They have to be the same element.
Wait, isn't it?
It must have different, okay, I can't read. Okay, so important that you read. They must have different, okay, mass numbers, but the same atomic number. So number 2 is 2. Just check to see you're paying attention. Okay? Which element is a noble gas? Noble gases, you should all know at this point in time, is the last column. Okay, they're the column that are most stable. They have the filled octets, okay, with the exception of helium. Okay? So krypton is Kr. Now, Mr. Zagrodzky, how do I know krypton? Okay, how do I know krypton is Kr? Now, if you don't know, okay, you have a nice reference table that, my friends in chemistry, is so underutilized, and that's reference table S. Okay? So, you know, krypton's atomic number what? 36. So you go to atomic number 36, scroll down. Okay, if you're just making sure that krypton is it, and lo and behold, okay, you'll see that krypton is Kr. Some people don't know that the elements are given to you for you there in table S. Rock on. Okay, so krypton is your answer, very simple stuff. Now, did I hear someone say, how do I know stuff's a gas? Did someone say that to me? Did I hear someone say, how do you know something's a gas? Yeah or no? Did someone say that? Let me show you where all your gases are. Yeah, you should know your gases. Here's how you figure out all your gases at STP. I think of it as the, I don't know, the backwards L rule. I don't know, L's for you, I'm a little whatever, but take this backwards L, okay, and you're going to run it across the periodic table top. So you got hydrogen, I can't draw straight, all the way down to radon, and that's my one backwards L. Then I've got Nafkal, and those are my 2 backwards L's. So my backwards L here, Nafkal, and I got this one here is all my gases. The 2 liquids, bromide and mercury. Everybody else is a solid STP. Okay? Something that could pop up. Moving forward. Now, number 4, as we would say in Riverhead. Okay, on the present periodic table of elements, the elements are arranged according to increasing. Now, the reason why they say present, because if any teacher has taught you about the reference table, Dmitri Mendeleev put this together based on atomic mass. At the time, in the mid-1800s, they only knew that atoms differed by their mass number. And people remembered that and say, okay, it goes in order of mass. A couple of them are rearranged based on their atomic number. So when we found atomic numbers or protons in the 20s to 30s area there, we rearranged the periodic table because some of them were not going in order of that. So it is going by atomic number. The periodic table is going in order of the atomic number. And some people love to put mass, and I just want to squelch that, okay? Because if you look carefully at some of these, they do not go in order. Okay, look at cobalt and nickel. 58.9, 58.6. When this was arranged with Dmitri, okay, nickel was here, cobalt was here. When they found the atomic numbers and came to the realization that this goes in order of atomic numbers, they had to switch these. Okay? So it's an order of atomic number. It's a periodic function of the atomic number. Okay, so number 4. Number 5. What's a property of most metals? You got to be able to understand that the metals are big radii, which means their electrons are so far away from their nucleus, they hold on to them loosely. So it's kind of like taking someone, I don't know, you're holding on to your little brother or sister, and you see something like, whoa, okay, so you have a little attraction for something. Therefore, electrons are so far away. Nonmetals are kind of like OCD for their electrons. They pull in their electrons and they fantasize about gaining more. Okay? They're small, they want them. Metals, the electrons like, yeah, whatever. Okay? And they tend to lose stuff because they're so farther away from the nucleus. So if you think with me that difference, all these properties make sense. They tend to gain electrons. No, metals are big. They become positive. You can't find me a metal. Here's my staircase that separates the nonmetals from the metals. Boron, don't be one. Silicon, arsenic, tellurium, and germanium. and antimony. These are my metalloids. Everybody at the top is small enough. These guys, my friends, are so big they tend to lose electrons. And you can't find me any of these that become negative. So they lose electrons when bonding. They're poor conductors. They're poor conductors of heat and electricity. That makes no sense. Think with me for a second. To conduct electricity, you need two requirements. This is a core concept. What are they? To conduct electricity is a good try. You have to have free-moving electrons or free-moving ions. If you guys are metals, your metal nuclei, and you have your electrons aren't held tight. Your electrons are so loose, it's like, hey, where's your kids at? Think of the electrons as your kids. Where's your kids at, man? I don't know. Your kid's over my house. I'm watching them. You got mine? Yeah, all right, yeah. The kids are able to, in this community, be shared amongst all of the families. I got my neighbor's kids now. They're fine, yeah. Electrons, what? The kids are free to move. So if I put something negatively charged in the community, and all the kids are negative, they're free to repel and move to the other side of the community, right? Someone moves in that's kind of shady, okay? Maybe he's on some kind of list or something. Everybody moves to the other side of the neighborhood. And you'd say the charge of the kids are what? Conducted because they can move. So, but if you're non-metals, kids are like right here. Dad, I'm 24. Stay right there. Okay? You're so OCD that your kids can't go anywhere, so you can't conduct. So you got to know that, visualize that clearly. They're great conductors of electricity because they have things who can move. Non-metals are terrible conductors. So obviously, big radii, electrons, so far away from the positive nucleus, they tend to lose, okay, when bonded. Just make sure I read correctly. 5 is 2. Number 6. What is the correct form for iron 3 phosphate? What the heck is that 3 there for? Yes, sir.
It's to signify the oxidation state of
Absolutely correct, because iron has 2 choices. It can be +2 or +3. So elements that are positive, that have multiple choices, could be the other one. So when you say iron phosphate, there's 2 possibilities, and you should know this. Different formulas give you different properties. So if I go to the chemical store and want some iron phosphate, they'd be like, well, which one do you want? Well, I don't know. Okay, you got to know. So iron is +3. For those that don't know, okay, check out iron. All right, up close and personal. Can you see that? There it is. All right, iron is +2 and +3. So you got to tell me which one. But there are some, by the way, there's transitional metals. One of their properties is they have multiple oxidation states. But my friends in chemistry, there are some metals, like the alkali metals or the alkaline earth, that only have one choice. So if I have sodium chloride, good enough, I don't need a number. Magnesium chloride, don't need a number. Iron chloride, which one do you have? So that's why that is there. So party people, back to the problem. So, iron 3. Now, people think this is the 3rd choice, or the other thing has to be 3. No, it means that iron is +3. Now, phosphate. What the heck is a phosphate? Now, do not pick phosphorus. That'd be ending in IDE. Anytime it's binary, anytime it's a non-metal at the end, you put an IDE. Chloride, oxide, nitride. But a phosphate, that's not an IDE, so I'm going to have to go to the what the heck is that table. What the heck is a phosphate? I call table E the what the heck is that table. So I go there. Maybe. Let's go there. What the heck is a phosphate? Table E. And I will have trouble with this. And of course a phosphate, okay, is right there, is a cluster of nonmetals that is bonding together. What kind of bonds exist between nonmetals? Covalent, correct. Why? Because this could be a part 2 question. Why do they share? You're right. That could be a right, correct answer too.
Because their difference in electronegativity is less than 1.7.
Yeah, now what does that mean? Actually less than 1.7, but good enough. What does that mean? Me and you are OCD for electrons. Okay, I need one to be stable, you need one. So it goes between us and we what? We fight for it. But we're both pretty strong, so we're forced to share. Right? Me and my evil twin Mongo, okay, have about the same strength. So we love to do family tug of war. So that tug of war is that electron in the middle. And we're both pretty strong. He's a little stronger, but never. So in any case, we pull on the rope. Nobody's strong enough to yank the rope away. Now I get mad because I can't pull the rope away. So what I do is when I go home that night, I would tug war with my 3-year-old. Now, I put gloves on his hands, but I pull the rope away. When I pull the rope away from my 3-year-old, okay, I step over him and say, "Who's your daddy?" No. That's like ionic bonding. I'm the non-metal, pretty strong for electrons, high electronegativity. And the kid who's the what? 3-year-old, my kid. Okay, once he's not crying, he represents the metal who lost the electron because he didn't have enough strength. Think of it that way. If you understand why, it stays with you. Good answers, though. All right? So in any case, this cluster has covalent bonds, which is important. So back to reality. Okay, up there goes gravity, and okay, so phosphate is PO4. -3. Hey, this thing is +3, this thing is -3. It's a 1-to-1 ratio. Now, is that an empirical molecular formula? Yes. Salts, metals, positive and negative ions make crystals. This is a solid. Anything you see positive, negative ions coming together, they're making a crystal. And if you have iron phosphate, what this means in the crystal, there's 1 iron +3 for every 1 -3 ion. Don't get lost and think that's a molecule. That's a salt. That's an ionic compound. What's the properties of that? What's the property of any ionic compound? They're solids. They stick together because of positives and negatives. They're what? Melting points are really high. If this could dissolve, it would be an electrolyte. Okay? Because it would have free moving ions. This is electrolyte when it's liquefied because the ions are free. You've got to see questions. You've got to look at this globally. Not just a question. Everything's linked together. There's your answer choice 3 moving forward. Number 7. I can do this. Number 7. The bond between bromide and Br is, okay, well we kind of covered this already. Bromide bonding to bromide is the same non-metal. It's me and my evil twin Mongo now. We're both strong for electrons. We're both OCD for electrons. And if you put them in between us, that's mine. Come on! But we're both the same strength now. So we're both forced to share these equally. That's key. We have to share these electrons equally. Stop it. Okay? Now, if we share these equally, that means we're forced to share. Of course, we're going to be covalent. Now, they don't get into too many details, but you should know this is a non-polar covalent bond, correct? They could ask for that. They didn't. Now, of course, it's covalent because they both have high attractions. They're both small. Me and my evil twin are pulling. So they're forced to share. Okay, and that's your answer, 3. But they could have asked, okay, is it non-polar? Is it covalent? Polar and non-polar are just covalent. Now, if me and my evil twin had different strengths, you're stronger. He'd be sharing electrons closer to him, and this would be unequal sharing. On this side of the bond, it'd be positive. On his side of the bond, it'd be negative. And you should know, non-polar covalent bond, we're sharing unequally because he's a little bit stronger. His electronegativity is higher. But in this case, this would be a non-polar covalent, sharing equally. So in any case, covalent, they're forced to share because they're nonmetals with 2 high electronegativities. Number 7, 3. Okay? Number 8, the amount of energy required to remove an outermost electron from a gaseous atom in the ground state is called ionization energy. Don't get lost with the first. The first just means I want to remove the first electron. So on table S, they list first ionization energy. And ionization energy is just that. How much energy does it take to yank an electron away from me? Make some guesses here. I'm a metal. I'm a metal. A big radius. Electrons are so far away from me. Takes a lot of energy? No, because I barely attract. In fact, sometimes I lose them and I don't even know. Okay? How about a non-metal? Try to take this away from me. Okay? It's going to take what? A lot more energy because I'm really, really attracted to them. You've got to get this. This is a major concept. Remembering ionization energy is important, but understanding the difference between small and the bigs, okay, is where most of your chemistry comes from. You've got to see globally. So clearly, okay, it's ionization energy. And they could ask you, who has more ionization energy? Carbon or fluorine? Who's going to take more energy to pull them away? If I give you these four, carbon, nitrogen, oxygen, fluorine, who's going to have the greatest amount of energy to pull electron away? Well, who's the smallest? Who's the most electronegative? So he's going to be the answer, or she. Okay? Now, if you don't know, table S provides that information as well. Okay, moving forward. Number 9. What occurs when an atom of chlorine and an atom of hydrogen become a molecule of hydrogen chloride? Okay, major concept here. When bonds are formed, why do atoms make bonds? To neutralize, it's more of an acid-base kind of thing. You might have the right answer, but you're kind of using vocab that I can't kind of accept. Become more stable. Now, stable, high energy or low energy? You got to get it. Stable means low energy. A rock on top of the hill wants to become a rock on the bottom of the hill. Yeah? So things in nature move generally towards stability. At the end of the day, do you guys do wind sprints? Okay, normally you don't. Okay? Normally at the end of the day, you get in front of the television, you text, you lay down, we go to sleep, we chill out. Okay? So elements are no different. So they want to become stable. The reason why chemicals bond is they use each other to become normally as stable as these guys. These guys are so stable, they don't want any electrons. They're inert. They don't react. So these guys react to become like these guys. So a chemical bond obviously is going to be made because you're dealing with atoms of chlorine and hydrogen who don't have any bonds. So a chemical bond is formed, and this gets lost in the shuffle all the time. When you form a bond, energy always is released. Why? Because you're becoming stable. If you forget that, doesn't it take energy to break something? So you go in the reverse, and they love to ask the reverse. If I take hydrochloric acid and I break it apart, they can write this question. I've seen it written so many different ways. I can write the question like this. If I have hydrochloric acid, 2 of them, and it becomes this, and sometimes they'll make it simpler, you would say, bond is broken. Sometimes just give you the H. And you would say energy is absorbed. To break a bond, it takes energy always. Why? Because bonding is low energy. It's a major concept you understand. If something is low energy, it's going to take energy to give it enough energy to break and be unstable. Atoms who are not bonded, and normally they would write it this way. Sorry, feeling tall. They would write it like this. Okay, so any case, clearly, the answer is a chemical bond is formed and energy is released because when you create a bond, you're creating stable. Stable, my friends, means low energy. How do you get to low energy? You release it. It's exothermic. Okay, number 10. Okay, which molecule is nonpolar? Now, this gets so abused. People confuse nonpolar and polar with the bond and the molecule. You have to differentiate between the two. Okay? So my friends in chemistry, here's what I'll do for you. So let's start with the bond. And I'm going to go quick. I have a crash course in bonding, but here's how I would do this. I want you to totally get this. All right? First of all, to be a polar molecule, I'm going to do some Shakespeare. To be or not to be. Polar molecule. You have 2 things. Number 1, you must have a polar bond. What is a polar bond? Yes? Yeah, they're sharing electrons but unequally. The one who is more stronger pulls the pair closer to him, and that's the negative side. Now why do we need a polar bond? Because, my friends, if I'm a polar molecule, I guess we're not friends yet. Okay, but if you're a polar molecule, what does that really mean? It means in your molecule, your 3-dimensional shape, you've got more electrons on one side than you do on another. It doesn't mean that you don't have any other side, but there's a huge amount of electron density. This side is negative because it has more electrons. This side is written partial positive because it kind of lost some negatives. There's an unequal distribution of electrons if you're a polar molecule. That's what it means. You have a negative side and a positive side because there's more electrons on one side. That's what it means. What creates an unequal distribution of electrons? A polar bond. So you have to have a polar bond that creates that scenario within the molecule. So number one, you have a polar bond because you have to have unequal distribution. Now, to be a polar molecule, okay, you must be asymmetrical. Why? Well, if you're asymmetrical, there's no way for your polar bonds to cancel themselves out or even out. For instance, okay, let's talk about methane. Does methane have polar bonds? Sure it does. It has 4 polar bonds, and very simple. 2 different nonmetals, and hydrogen is a nonmetal because it's a small, not a big. Okay? Hydrogen and carbon have two different nonmetals. They're sharing unequally. These are 4 polar bonds. Okay? At least in the New York State curriculum. Okay? Now, because it's the same all the way around, it has symmetry. And what happened? Well, because it's symmetrical, the 4 polar bonds cancel out. But why? Well, if you're unequal distribution of electrons in this direction, and your unequal distribution of electrons in all directions, isn't your unequalness become the same? Doesn't your unequalness become equal? And who has different amount of electrons? No one does. So this is a non-polar molecule with polar bonds because it has symmetry. The symmetry made the unequalness equal in all directions. All you have to say is, hey, it's symmetrical, it is non-polar. So, who has polar bonds? Well, aren't these all 2 different nonmetals? So they all have polar bonds. 2, who is asymmetrical? All right, well, we're looking for a non-polar molecule, so we're looking for something that is what? Symmetrical. So water is not symmetrical. You should know water is polar just from being in any chemistry class. Water is bent, right? So that molecule is not symmetrical. Ammonia looks like this when you do a Lewis dot diagram. Has a lone pair up top. That's not the same all the way around. CO2, my friends in chemistry, okay, let's do right here. You do a Lewis dot diagram, it's a linear molecule. So it's symmetrical on both sides, and then therefore CO2 is symmetrical, therefore it's nonpolar. Carbon monoxide is just C and O, that's asymmetrical, asymmetrical, asymmetrical. This is the same on both sides. And we know it's linear because it doesn't have a lone pair to bend it down. This would be linear, but these lone pairs repel electrons down into an asymmetrical shape. So, because it's symmetrical, the polar bonds on both sides, and there's 4 of them, are canceled out, or they're the same. So the answer is the nonpolar molecule is the one who is symmetrical. Okay? See this question all the time, but you need to know the difference between polar bonds and polar molecules. Don't think everything polar, it's polar, I think, symmetrical. That's not going to work for you. You have to think bonds and molecules, how they're different. Okay? And all the explanations I went over are part 2 explanations. They just present it weird with a blur. Okay? You hang on, we'll get to those. So number 11. Please stop me if you have a question. Or you didn't get it, or I was just being too tall. Okay? Most of the time I'm too tall. So I guess, it's up, I think I wiped it out. Or did I wipe it out? Yeah, I did. Yeah, okay, gracias. Okay, yeah, who's a mixture? Yeah, now a solution is a mixture. Now, just be careful, party people. You should know that a solution is aqueous, and it's called a homogeneous solution. Why is it called a homogeneous solution? The first drop is the same as the last. Do you hear dissolved? Do you hear aqueous, completely dissolved? The first drop is the same as the last, and the solution is a mixture the same throughout. Careful with the gas. Okay? They could put air here. Okay, although I know they wouldn't because that would be 2 choices. But air is also a solution. It is also a homogeneous mixture. Okay, why? Air, all the gases equally what? Mix. And for good reason. Because I could just be minding my own business and walk into a pocket of no oxygen. That doesn't happen, okay? So air is also a solution. Be careful, that could pop up. All right? Number 12. I don't know what I said. What did I say? I don't know. Number 12. 12, buddy! A bottle of rubbing alcohol contains both 2-propanol and water. These liquids can be separated by the process of distillation. Hold on. I've got water and 2-propanol. It's telling me it's a solution. It's a mixture. You should know mixtures are made physically, and they're separated physically. They're not chemically bonded. Okay? Distillation is a process where we can use the individual properties of a mixture to separate them. If you've got a mixture of liquids, they retain their individual properties because you're not making a new compound. So if I've got water and 2-propanol, water still has its boiling point at about 100. And of course, 2-propanol has its boiling point probably less than that because they're not bonded. When they start bonding chemically, then they have brand new properties. That's why sodium chloride, table salt, when you pop it in your mouth in a French fry, you don't explode and die. Because sodium chloride is made of pure sodium. In water, pure sodium explodes. Pure chlorine is basically the main ingredient in mustard gas, which is pretty toxic. So you have salt, NaCl, in our bodies, and it's not harmful to us because it's Na+. Na lost an electron to become as stable as neon. Chlorine gained will be stable as argon. So they're stable forms. Okay, so in any case, process of distillation. Combining chemically means that there's a compound. This is a mixture, so get rid of 1 and 2. They love to understand the idea that mixtures are made physically. Chemicals are made by bonding, and you change your properties that way. So, 1 and 2 gone. Have combined physically and retain their different. No, have combined physically and retain their individual boiling points. Choice 4. Yeah, I have those tests there. Number 4, as we would say, North Riverhead. We actually don't say North Riverhead, we say no head. Okay? All right. 13, compared to pure water, an aqueous solution of calcium chloride. All right, this is my thumbs question. You want to get to the chemistry part. You knock, knock. Someone slides a little slide and looks out. You got to give a secret handshake and see the symbols. Yeah. I don't want to do this in front of the door, so do it like this. Okay? No one's there. How does that work? The higher temperature is the boiling. What does it always do? Goes up. Lower temperature is the freezing. What does it always do? So anytime you add solute particles to water, the what? Boiling point is elevated, the freezing point is depressed, always. So, compared to pure water, a solution, that's something with water, is going to have a higher boiling point and a lower freezing point. Always. They love to ask about this in part 2. This is a part 2 question, just manipulated to be a multiple choice question. Now why? Why? Why is that true? If I add solute particles to water, why is the boiling point elevated? To me, if you understand a little bit of the why, it's not just memorization. Okay? So why? Well, my friends in chemistry, or my enemies if you hate this. If I have water, of course water is blue, right? Now, add some solute particles. These are things dissolved. Guess what? They get in the way of water trying to what? Evaporate. They're in the way. So you need more heat to give these particles enough energy to get around the obstacles, so the boiling point is elevated. And it's harder for these guys to freeze. I'm trying to get to the position where I make a crystal. They need a colder temperature to make it freeze. So they resist freezing and resist boiling. Just remember that. Okay? The solution with the solute particles makes it tougher to boil, makes it tougher to freeze. That's why you throw salt on ice. You lower the freezing point. Now the freezing point's now lower. It begins to melt because the ice with a lower freezing point makes the air temperature feel like it's warmer. Love to talk more about it, but we're moving forward. So we got a higher boiling point and lower freezing point. Aqueous solution always is a higher boiling point, lower freezing point. If you remember anything, remember the fingers. Okay. Number 14. What a Fiat saying, sprechen Sie Deutsch. Okay, 14, I can do this. Maybe. Move it up and down so it really bugs you. Okay. Under which conditions does a real gas behave like an ideal gas? People get this all the time wrong. I want you to remember that a real gas is like a real student. An ideal gas is like an ideal student. Okay, there's a set of postulates. Let's just cover them quickly. Sometimes they call them kinetic molecular theory. And they outline how an ideal gas should behave so that our formulas work out perfectly. Now, to be an ideal gas is like an ideal student. The ideal student, and let's put these things down. Okay, and I'm going to go through this quickly. I'm going to go through it because I don't want any student to ever get this wrong. Okay, so let's just make some room here. Oh, Mr. Unstable, I will not do today, no. I can move this down maybe. Okay, good enough. Oh, no, it's the wrong question. Feel bad. Okay. Now let's get rid of this guy. All right, cool. Let's get him. Okay, so there are 4 postulates here. Number 1, to be an ideal student or an ideal gas, it's the same thing. First thing, okay, the ideal student is so focused on the teacher. It's like a peregrine falcon looking at its prey. Hopefully they don't lick their lips, okay? Now, if someone asks this student a question, Mr. Grotsky, Ben, could I have a pencil? I like turtles. Okay? They're random! These people are random because they're so focused on the teacher. I want students. This guy is weird. Okay? Now, they also go in straight line motions. You pick that ideal student to go get the, can you please get the, yeah, sure. Can you get the worksheets on the printer? Yeah. They go in straight line motions because they want to get there quick and come back because they don't want to miss the lesson. So they're fast. They go straight line motions. They're random people. Okay? Now, 2, when they bounce into things, they're elastic collisions. All their book bags and all books for the courses they're taking this year and last year are in their book bag. So they're really heavy and they bounce into people. The bell rings, they go right to the door, they hit people, they bounce off. They're elastic. 3, they tend to be smaller. Okay, so they have small volumes and they're really fast. And this is the big one. Number 4 is the big one, I think. Number 4, think with me, an ideal student could have People Magazine's Most Beautiful Person 2013 here, 2012 here, and they'll have absolutely no attractions to them. They have no attractions to the people around them because they're so focused on the what?
Teacher.
Right. Now we got a real student, a real what? We got a real gas. Number 1, not so random. How's it doing, Ben? You have a pencil? Yeah, what's going on? Yeah, I got a pencil. Yeah. Stop talking! Okay, well, they're not random because they're on point with their conversation because they're social. They don't move in straight line motions. Ben, can you go get the worksheets? Instead of going directly to the printer, it's like, hey, what's up? How you doing? They do what? They bend and curve toward the other students to talk with them. They get the worksheets finally, and they come back again, what's up, how you doing? And they moved in curved line motions because the biggest thing, real gases really have attractions. Really have attractions. They're social. So if you remember anything at all, real gases are really attracted to each other. So they kind of are not independent gas particles. Our ideal gases, laws that you learn, mean that gas particles are totally independent. But guess what? That truly doesn't exist, only on certain conditions. Most gases have some attraction. So their volumes are bigger, they go slower, they're elastic collisions, but the biggest thing is they have volume and they have attraction. Let's go back to the question. Under which conditions does a real gas behave like an ideal gas? So I'm going to take a real gas who really has attractions and make it an ideal gas who ideally does not have attractions. I call this the hand question. So a real gas really has attractions. And I want to create a scenario where they don't have attractions anymore. What am I going to do with pressure? If I increase the pressure, I push them together. So I want to do what with pressure? Decrease the pressure, which means they'll have less attractions. So I decrease the pressure. And what do I do with temperature? You should know temperature is motion. Should I slow them down? Or should I speed them up? You speed them up, they have less chance of attracting. So their pressure goes down and their temperature goes up. And if I go the opposite, ideal gases have no attraction. How do I make them into a real gas? Push them together. Increase the pressure and slow them down. What happens to gases when you slow them down anyway? When a hot gas hits a cold air, what happens? We make fog. The gas condenses. Why? Because they eventually attract. That's why all gases are real to begin with. We try to get these ideal conditions. Okay, so the answer is, how does a real gas behave like an ideal gas? A real gas really has attractions, so to make them have no attractions, we're going to lower the pressure, and we're going to increase the temperature, choice 4. That's how that works. My hope is you understand these silly stories and apply them to an ideal and real gas, because this is a major concept that seems to be on almost every test. Almost every is kind of a weird word. Okay. 17. Did I skip 16?
Yeah.
All right. Let's be crazy and go in order. Yeah, the one I wiped out. Yeah, gotta be on top of me. Tend to make these silly errors. Okay. Who has this structural formula? Okay, what is it? Let's read the whole question before we get started. What is the IUPAC name with the compound? IUPAC is just that naming system you learn for all things. Compound with the following structural formula. Okay, well, I see a carbon double bond to an O. I see the rest of an organic compound here, and the rest here. Yes, sir. Okay. So my friends in chemistry, this is an R, and this is an R prime. And if I go to table A, who's got a carbon double bond to an oxygen in the middle of the compound? A ketone. 1, 2, 3, 4. So we start with bute. There's single bonds between the carbon. Do not think because it's a double bond with the oxygen, it's an ene. Anes or enes or ines are for the bond between the carbons. So we have 4 bonds. That's a bute. It's a butane because they're single bonds, and the one is for a ketone. And it's directly from table R. Let's just go to there for reviewing pleasures real quickly. Let's get out of what the heck is that table. Sometimes I can do this fast. Okay, so there is our ketone, and there's the example they give you. R prime means the rest of an organic compound, a hydrocarbon on one side, hydrocarbon on the other. Look at the example they give you. Ends in -one. Pent, okay, is 5 carbons in this case. The ane is single bond. So they give you an example. For those who just waltzed in because you're at country, probably smoking. Okay, here is the examiner going over. Why anyone ever smoke? Makes holes in your clothes, makes your teeth yellow, stunts your growth, and got bad breath. I'll sign up for that one. Okay, but I look cool. All right, and you die early. Yeah, it's probably a big one for me. I like life. Number 16. Which system best explains the role? Did I answer that? Yeah. Butanone, choice 3. By the way, how do I know it's bute? Table P gives me the names of the prefixes. Number 16, which statement best explains the role of a catalyst in the chemical reaction? Okay, I think catalyst, I think of 2 explanations. It lowers my activation energy because it medicates the hump. Okay, finds an alternative pathway. So when I think of activation energy, I think of potential energy curves. So here's one. It's an exo or an endo curve. Exo because I'm starting high, going low in energy. Anytime my energy drops because I'm releasing it. Kind of like when you bond. Create a bond, your energy drops, so energy is released. So a catalyst, my friends in chemistry, okay, does something. It creates a whole system of new reactions that makes the whole process lower in energy. I always say that it medicates the pimple. Okay, so this is unmedicated, uncatalyzed. This is medicated or catalyzed. You should know that that activation energy is from where you start to the top of the hill. And guess what? This is a lower activation energy. So it lowers the activation energy. So if me and Noah, we're going to have a race to see how many rides we can make with a slide, and he's got a 20-foot slide and I've got a 3-foot slide, in 10 minutes, how many rides can we make? I'm going to get a lot more rides in. Because it takes a lot less energy for me to climb my slide than it does for Noah. Besides that, it's kind of unfair. Two rides in the slide, okay? If it's a 3-foot slide. Okay, any case. So, Catalyst limits the amount of reactants used? No. Chemist changes the kinds of products? No. Catalyst provides an alternative reaction pathway. This is the pathway that requires less activation energy. And that's something to really just circle and understand, because how many times do they ask about a catalyst in part 2? Those who just walked in, I want you to understand that we're going over not just a question, the concept behind the question, because they ask the same, they look for the same answers in these tests, but different questions. It's the same concept over and over. Just because we're in a multiple choice section doesn't mean I'm not going over concepts that are in part 2. Okay? So that's the answer there.
So exothermic requires less.
Exothermic reactions require less activation energy, correct, because they're already unstable. Remember, activation energy is where you start to the top of the hill. If you're stable, you're going to need a lot more activation energy. Why? Because you're lower energy already, correct. By the way, what's this right here? The difference where you start and finish. Delta H, the heat of reaction. Does a catalyst change that? No, it doesn't. It does not change where you start to the top. Where you start and where you finish. That change, look at it, goes down. That's why delta H is negative. Okay? Good stuff. Maybe. A lot of fun. Maybe not. We'll do this Thursday if you want. Okay? This is so much fun, isn't it? 17. The rate of the forward reaction is what? This is equilibrium for the millionth and one time. There's two things you got to know about equilibrium. The rate of the forward equals the rate of the reverse. And because of that, the amount of the reactants and products stay the same. If I've got a water bottle, can I use your water bottle? Okay? Now, I know we can't see it, but so if we invert it, there's our line. Now, the rate of evaporation equals the rate of condensation. So this is called phase equilibrium. And we can stand here till Thursday. Maybe Friday, that'd be fun. And we can watch that line. And guess what? It won't change. Why? Because as fast as we make gas, hope so, the gas becomes liquid. So you got to know that at equilibrium, the amount of reactants and products stay constant because of that. Thank you. So I always say, hey, I got 10 people at the door. I got 2 people here. I got a line of 10, line of 2. I make every person switch lines every minute. One line, one person per each line every minute. Come back in 10 minutes, what's happened? People have changed lines, but the number of people each line has stayed constant. So those two things, rate of the forward action is less, equal to the rate of reverse. Didn't mention it, but that's the process. Do never say that the amount of products and reactants are equal. It's to how fast they go. Okay? So number 17 is 3, easy as pie on a Sunday afternoon. 13, unless you don't have pie, then it becomes difficult. Which statement best explains why most atomic mass in the periodic table are decimal numbers? Why is there decimal numbers on atomic mass? We know that the atomic mass of a neutron is 1 atomic mass unit. The atomic mass of a proton is a 1. But when I look up for carbon-12, it's 12.001 something. Why the decimals? This is an important concept. Right, it's the average of all the isotopes. But wait a minute. That seems to be silly to me too. If it's the average of all the isotopes, let's get out of here for a second. Let's go file new. Like for instance, carbon-12. And carbon-14. As we would say in Boston. Boston, because I'm from Long Island and I drink coffee. Coffee. Okay? I go to Boston. Okay? Now, it's Boston. Now, any case, listen, these are isotopes. If I do an average between 12 and 14, what do I get? 13. But you look for carbon in your reference table, or your reference table, as I poorly described. Okay, if I knew my alphabet, I'd be better at this. Okay, let's look at carbon. Let's get up close and personal with carbon. I know it's there too, but... something's not working. All right, so look at carbon for a second. It's 12.011. How come not 13? Because... nope. Electrons actually are... electrons have mass, but they're so tiny. It's a good guess, though. The two that... right, carbon-12 occurs a lot more, like 99.9% of the time. So what they're talking about is something called the weighted average problem. And it's a problem that they're implying about, but not actually doing. Well, let's do this. Let's pretend I'm tall, and we can do this weighted average problem. Now, a weighted average problem is just like the problems, just like the averaging we've done already. Like if you want to find a straight average between 12 and 14, you know it's 13. You would take two numbers and do what? Add together and divide by what? Don't ever do that for a weighted average problem. But that only works because you're saying what? You're saying 50% of carbon-12 is carbon-12 and only 50% is carbon-14. Now, if 50% is carbon-12, let's find 50% of 12. 12 times 0.5 is what? Let's find 50% of carbon-14. 14 times 0.5 clearly is 7. And you add them together. Look at that. When you do a straight average with two numbers, you're saying they're equal what? Of abundance. Now, if you're going to do a real weighted average problem, we know that just like, what's your name? Ingrid? Chloe. Courtney. I just made these names up. If they're 99% carbon-12, then this number would be 0.99. And this must be what? 1%. I'm just making these numbers up. This would be what? How would you find the percentage at 1%? 0.01, right? Right? I want to find a new dress. Move decimal place 2 places over. And I'd find these percentages and add them together, and these numbers would be close to 12. So on the periodic table, all the numbers on the periodic table round off to the most, what? Abundant isotope. So back to the periodic table. Okay, so you go to carbon-12. Why isn't that working? Okay, so you go to carbon-12. The most abundant isotope is 12.01. That's because of the averaging. What's the most abundant isotope of boron? Don't be one. Get this right. Boron. Its most abundant isotope is boron. No. 11. Most abundant of aluminum. Aluminum. Right. Okay. So because of the decimal places. Okay. It's because of the averaging of all the abundant isotopes using their percentages in nature. Can't say enough how important that concept is. That's why I spent a little bit of time on it. Okay. Moving forward. So atomic mass determined relative to H1. No. Atomic masses are weighted average of the natural occurring isotopes. Okay, so number 3 is your answer. 18 is 3. For those that just walked in, I'm doing the test January something. It's over there. Okay, number 19. Order 19. Bless you. 19. All organic compounds must contain the element what? If you're organic, my friends, you have to have carbon. Right? Everything that's organic starts with the prefix of how many carbons in table P. Meth, F, pro, but. How many carbons and carbon chains? Moving forward, 19 is 3. Doing trouble with this one. Tomorrow's going to be really hard for you. 20. Which of the following compounds has the highest boiling point? Okay, well in table S, they do give boiling points of elements. These are compounds, so not going to help you. Now some people I've known to take the elements and add them together, the elements boiling points and add them together to come up with the boiling points. Don't do that. What they're after here is this concept. What kind of attractive forces? When something boils, that means the molecules are separating from each other. They're overcoming these attractive forces. What kind of attractive forces do you think these guys basically have? They're polar, and they have an H. They have H bonding. Now water, you should know this. Okay? And they can make you draw this. You're due for a good drawing. If you look at, let's wipe this out. Keep doing that. Let's wipe this one out. Okay, so move this forward. Here we go. Look at water. It's a polar molecule, as we just went over today, negative and a positive side. This positive H attracts this negative part of the water molecule. Now, why is it polar? It's got a negative side and a positive side. The positive side attracts the what? Negative side of another molecule. This is called an H bond. It's the strongest type of attraction. The reason why water resists boiling, the reason why water resists evaporation compared to other liquids, because it has strong intermolecular attractions. So if you look back at your choices, what's happening to the polarity of the molecule as we go down? What's happening to the difference in electronegativity here? Notice I have oxygen, sulfur, selenium, tellurium. What's happening? Yeah, the electronegativity difference is increasing? Decreasing. This is more electronegative, this is less electronegative. I really should say, are they getting more polar or less polar? Yes, polar, because the electronegativity difference is decreasing. Hydrogen is about 2.2 electronegativity. Oxygen is about 3.5. As you go down, what happens to the size of the radius? And if you understand that, the radius gets bigger, electrons are farther away, you attract them less. So if you attract them less, these molecules have less polar bonds. As we just talked about in this test, that means they're less polar molecules. What makes a polar molecule? An unequal distribution of electrons. So, the highest boiling point would be the one who has the strongest intermolecular attractions, who is the most negative, who is the most positive, who sticks together strongly, and that'll be water because it has the greater difference in electronegativity. Now, where are the implications with this? They are in Table H. Table H? What are you talking about? Look at Table H. And I'm here to show you, and by the way, for those that just walked in, okay, I have a crash course that I made over the weekend for the review of all the reference tables. For those that know what a crash course is, go to my website and under review, I have a crash course for every single unit. But remember Table H? You guys worked on this months and months and months ago. Water has a lower vapor pressure. Why? It resists evaporation. Why? What kind of intermolecular attractions does it have? The forces of attraction between molecules compared to propanone have to be stronger, which means its boiling point is higher. It needs a lot more heat to make it achieve boiling than it does for propanone because of the weaker, stronger attractive forces. I know I did it, and I know Mr. Deal did it. Took 3 liquids in my fingers. I wiped them across the desk. It was propanone, ethanol, and water. This guy evaporated right in front of our eyes. This was second. This guy resisted the most. That's why it's the highest boiling point, stronger attractive forces. And of course, the lowest vapor pressure. Vapor pressure is the force of liquids escaping into the gas phase. You can look at this line as the rate of evaporation. In any case, that's the implications that we're getting at in that question. So obviously, water has the highest boiling point. It's the most polar. 22. Best conduct electricity. Hello, to conduct electricity, what do you need? There's 2 things you have to know for this test. Free moving what? Electrons or free moving ions. Okay? When ions are free, you have a solution of something that's a salt. It's called an electrolyte. But these are just elements. So this is the question is, do you know which one is the metal? Okay, we've got nickel to the left of my staircase, and the rest of them are nonmetals. So sulfur, nitrogen, bromide are terrible conductors. Why? Their electrons are OCD, man. They're not able to move. That's why these guys are great, what? Insulators. Their electrons aren't free to move that much, so they can't conduct heat electricity. So of course, my metal is the answer choice 4. 20. I skipped 21. Thank you. I get so tall and crazy. Mostly crazy and tall. Mostly tall. Actually, I got that a long time ago. So I'm not even used to that yet.
What, being tall or crazy?
You decide. 21. The functional group, Cu. Okay, Cu comes from this. The Cu group is our organic acid. Kind of gave it away. What do I know? As we say in New England, table A. Go to table A. Okay, table A. There we go. I don't mention the Cu group, but if you look carefully, organic acids have a COOH ending. Rest of organic compound, this is the answer. I don't know what else to say, but they love to pick on organic acids. These are the only organic compounds that are electrolytes because they produce what? Free-moving ions. Right, an acid breaks apart into ions. Acids, bases, and salts break apart into free-moving ions. So that's an electrolyte. They love to pick on organic acids. When in doubt, pick an organic acid. All right, moving forward. Just pose it backward. Okay. Number 22, am I good? Keep me in check. We good? Oh, you did 22. You went backward, that's why I'm confused. Okay, 23, yeah? Yeah. Okay, moving forward. I said moving forward, I guess I lied over before. Okay, who undergoes reduction? Okay, this is, first of all, is this a redox reaction? Yes, how do you know?
It's
Right. Now, for my students, I always said to identify a redox reaction, find me a zero. A zero is a what? It's an element, which, by the way, is an atom. Why are atoms neutral? Getting back to our first question in this test. It's showing how all things are connected. Why are atoms zero? Protons equal? Right. So this is zero, and this is a zero. So if you find yourself a zero in a redox reaction, or a reaction, you know it's redox. So if they say in part 2, what kind of reaction is this? Now, you could say single replacement. You could say redox. But I know it's redox reason because I see a zero, which means if it's a zero on one side, it's not a zero when it's in the compound, which means oxidation numbers are changing and electrons are being passed away. Okay, now who's undergoing reduction? Okay, well, reduction means what? Leo the Lion says what? Gur. Okay, that really is helpful. Sounds silly, but Gur. Gaining electrons is reduction. That sounds weird. How can you gain something called being reduction? Because you're gaining negatives. If you gain negatives, electrons are negatives, your charge drops. So I want to find whose charge drops. Okay? So one way to do this is assign oxidation numbers and write a half reaction. Or you can do this even quicker. What can only a standalone metal do? What can only metals do? Can a standalone metal ever become negative and gain electrons? No. Metals can only lose electrons. Now, metal ions can gain electrons to reform the metal, but standalone metals can only oxidize. So I know clearly this guy is getting oxidized. So who's getting reduced? The iron in that compound. Because he's going from something positive to something zero. Positive going to zero, your charge is what? Dropping. Your charge is dropping because you're gaining electrons. So it's the iron. The question is, what's the charge? Well, it's not iron zero. And now, in these questions, and I'll do it the half reaction way in a second, but I'm showing you which way to say it. Oh, he's getting oxidized. He must be getting reduced. O is -2, so he's neither getting oxidized nor reduced. So clearly it's going to be iron. The only one with a charge is iron +3. And how do we know it's +3? Because I have 3 oxygens. What's the charge on each oxygen? -2. Watch how I do this, party people. I know you guys, there's only one choice, but -2. There's 3 of them. What's the overall charge? -6. For me, how I taught this, the bottom numbers have to equal 0. So what charge overall do I need to iron for this to be 0? 6. +6. Because there's 2 irons, what's the individual charge? +3. And +3, my friends in chemistry, watch. Iron +3 goes to iron 0. Both sides of a half reaction have to have the same charge. So how many electrons and where do they go so that both sides have the same charge? On the right. Now if you put them on the right, here's your check. A -1 + 0 is what? A -3 and a 0 is what? -3. This side's +3, so you didn't do it right. That's your nice check. So I put it over here. 3 negative and a +3 is a 0. This side is 0. Both sides of a half reaction have to have the same charge. By the way, when you're choosing reduction half reactions, here's how R for R. The electrons are in the reactant side. Like that? The electrons are in the reactant side for gaining electrons, reduction. Because you're gaining them, kind of like gaining heat when it's endothermic. Okay? So iron +3. Now something else I want to say. When you get these types of reactions. I know I got a lot to say. Sorry. Always pick from this side. Always pick from this side. Always pick from this side. Always pick from this side.
Okay.
You should never pick from this side. If it's a redox reaction, I want to know who lost and who gained. If I was teaching somewhere else, maybe I'd say, I want to know who bought and who sold. Okay? I could care less about the other. So when you're asking for redox reactions, don't pick aluminum +3 and don't pick iron. Who gains? This guy gave its electrons to this guy. Okay, number 24. Clear? Somewhat? Fuzzy? One day I'll learn this. I'm just making this stuff as I go along. 24. Which energy transformation occurs when an electrolytic cell? Electrolytic cell, is that the battery, the one that needs a battery? That's right. The word electricity is in there. Voltaic cell. Galvanic cell. Alessandro Volta was the guy who made the first battery. So voltaic cell. So this needs electricity to make it occur. This is a non-spontaneous reaction. It requires energy. So it takes electrical energy and it makes chemical energy. Electrolysis is usually used to make a chemical reaction occur from electricity. The battery supplies the electricity. So it's, yes?
If it was asking for voltaic, it'd be number one.
Yeah, the chemicals make the electricity. Correct. Good job. So 24 is choice 2. All right. 25. Which of these pH numbers indicates a highest level of acidity? Okay. pH is low as you get more acidic. I mean, there's a great way to remember this. If you want to go into more detail, you don't know, anything above 7 is basic, anything below 7 is acidic. There is some reasoning behind that, okay? I'm not going to get into that right now. If you want to, you can look at the crash course in acid and bases for more details. But you should know everything lower than 7 is acidic at this point. 26. Oh, by the way, since we're here, if I'm going to go from a pH of 5 to 3, what's happening to the amount of acidity? It's increasing how much? From a 5 to 3. 100, right. Every movement of a single integer of a pH is a 0. It's a logarithmic scale. pHs really are exponents of base 10 logs. So you go from a 1 times 10 to the negative 5 to 1 times 10 to the negative 3. This 1 times 10 to the negative 3 is a pH of 3. And it's more acidic by 100 times. So each single movement of a pH represents a 0 in a base 10 movement. If I went from 5 to 8, the acidity decreased 1,000 times. The same thing as saying 1 over 1,000, or the basicity increased 1,000 times. Because 10 to the 3 is 1,000. Okay, 5 plus 3 is 8. So that's something to keep a hold of. 26. According to Arrhenius theory, when a base dissolves in water, it produces what? Oh my gosh, they gave me a name? I hate when they give me names. Well, guess what? Don't worry about Arrhenius, because this is the easiest definition to remember. To be an acid, in this case they want a base. What's the easiest way to remember a base? What are bases? OH minuses. So OH minus is the only thing, and that's it. Choice 2. If they said acid, what are you looking for? H pluses in solution. That's it. It's the easiest definition. Now the other definition is the Bronston-Lowry. They don't mention it by name. That's when you donate an H plus if you're an acid and accept a proton if you're a base. That one's easy to remember too, because if you're a base, just by the easiest definition, what do bases do when they get neutralized? What do they become? Water, right. And how do they do that? They accept a what? A proton. So the Bronston-Lowry base, or the other, they don't mention by name, is you accept a proton. Okay? And if you're an acid, you donate a proton. So it's very simple. So OH minus is the only negative ion. 26 is 2. 27. Which compound is an electrolyte? What are the 3 things I need to be an electrolyte? Why? And how many times have I mentioned these problems, the implications of things that can electricity? Either free ions or free electrons, right? It's all over these tests, part 1 and part 2. But if I'm an electrolyte, I make free ions. Acids produce protons, bases produce hydroxides, those are ions, or salts that are soluble. So who's an acid, who's a base, or who's a salt? First off, is that a base? No. That's an alcohol. That's an R with an OH. These are what? Non-metals bonded to each other. This does not break apart into ions. Just because you see an OH, don't think base. If you go to table A, okay, this is an alcohol. They love to throw alcohols to get you all crazy. You need a metal, an Na, an Li to make this ionic. Okay? This is glucose. All nonmetals. Doesn't dissociate into ions. Things that are molecular, things that bond to themselves into molecules, things that make covalent compounds normally are not electrolytes. Also a molecular compound. There's my salt. Acid, bases, or salts. How do I know it's a salt? It's ionic. Metal, nonmetal. Non-metal, non-metal. Non-metal, 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 non-metal. Non-metal, non-metal, non-metal. Non-metal, non-metal. Say it fast, they lock you up. Non-metal, non-metal, non-metal. Okay? Metal, non-metal, ionic, a salt. It's soluble. It breaks apart into ions. Since we're right here, and I can't help myself, what would this look like in water? If I was to draw the attractive forces, this is going to dissociate into calcium plus and Cl negative. What would this look like in water? I'm giving you all the implications of everything tied together. By the way, this would be a solution. It'd be an electrolyte. How would water surround it? I call this the famous boyfriend, famous girlfriend scenario. So I'd have the negative part of water, which you should know is the oxygen end, the more electronegative end, surrounding the positive ion. And I would have the what? The positive part of water, which is the positive end, attracting the negative ion. That's called molecule ion attractions. I call it famous boyfriend, famous girlfriend. Justin Bieber and Selena Gomez go hand in hand down the street in West Hampton Beach. There's 1,000, they go into the gym during the pep rally. No teachers. They probably get bum rushed. Okay? All the girls surround the guy, all guys surround the girl. Okay, maybe there's a few exceptions, but it doesn't matter. Okay? And then what you have is them separated and pulled apart. Okay? 28. Spontaneous nuclear decay. Spontaneous means that it happens just like a battery happens. You set up the chemicals and they're correct, they spontaneously produce electricity. A battery does not need a battery to make it happen. Okay? This is not spontaneous. This is called artificial transmutation. This requires this to be collided with aluminum. You do not go into a field to go pick flowers, look at the nice brook, pet the fish, look at the birds and the ospreys, and then go into the next field and see a particle accelerator sitting there. That's not natural. Okay? You see two things in the reacting side. They need to be collided to make this happen. That's not spontaneous. That requires an experiment that man has to build to create that. Pick some flowers and I tripped over the particle accelerator. It doesn't happen. Okay? It's not in nature. This, my friends, is a what? Is a regular chemical reaction that's dealing with electrons. This is not nuclear. They love to spill chemical reactions. And again, what did I say when we started this? Know where you are in the test. It goes 1 through 30, and it goes from atomic structure to nuclear. You're in the nuclear section. Pick nuclear reactions. These are about electrons. So 1 and 2, cross them off. I need to see how the nucleus changes. So this is artificial transmutation, not natural. And this is called natural transmutation. By itself, strontium, because why? Why does strontium give off a beta particle? Why? By itself, without any help. Strontium is naturally unstable. Its nucleus actually has too many neutrons. You don't have to know that piece. But nuclear reactions do their things without any help because their nucleus is unstable, has high energy. Things with high energy want to do something. And they release that particle to become more stable. So that's choice 4. It's a fancy way of saying which one was natural transmutation. 29. The stability of an isotope is based on its... Okay? Well, this is a really great question. There are basically a couple reasons. Number 1, protons. You should know that anything beyond atomic number 83 has too many protons. Protons are tiny, they're positive. They're stuck together in this nucleus. Neutrons help buffer the positive on positive. As you know, positive and positive repel. But too many positives in a small area, as Rutherford states, is going to create a scenario where they're not going to exist very well. So on the periodic table, anything beyond, okay, bismuth is radioactive. There's just too many protons. But it's not the only reason. If that was the case,